This is the CIsLunar Experience. I'm your host, J. Vincent Maroli. Man, a mere inhabitant of the earth, cannot overstep its boundaries. But though he is confined to its crust, he may penetrate into all its secrets. That was a quote from Jules Verne, a pretty awesome author from back in the day, who wrote amazing stuff about exploration and the future and some space things. Think that's fitting for today's guest, who is the founder and CEO of Honeybee Robotics, Kris Zacny. Welcome to the show.
Thank you. Appreciate that. Appreciate the opportunity.
Thanks.
I'm not CEO though.
Oh shit! I did say that wrong. Oh my god.
My boss is gonna fire me. It's okay. I'm just a lonely VP, and but the most important thing is I'm having a lot of fun, and it's really great place to work. And the company actually started a long time ago, almost 4 decades, in Manhattan by two friends who went to school together, and one day they decided to try to change the world. And one way to do it is go into robotics. And a few years after starting the company, so it was Kris and Steve, Kris Chapman and Steve Gorevan, and Steve caught a space bug.
Okay.
And there was a beginning, and there was no turning around. From this point onwards, it was all about space and developing things to go to space and explore. And 40 years ago, it wasn't just like the way it is now. So going to space was extremely, extremely difficult. And if you got to fly something to space, you were very, very lucky. Whereas now, it's we take it for granted how far we came along.
Yeah, we do. That makes a little bit more sense because we first interacted, a few months ago when I was in the program at Colorado School of Mines, and then more recently at a space resource conference.
Mm-hmm.
And then as I did this research, I saw Kris and the founder, Kris. And so I realized in my head, I conflated the two of those like a dork. So, hey,
yeah,
learn from your failures.
As long as I'm not going to get fired, so good. Yeah, no, and so in 2010, Gail Paulson and I left Manhattan. We used to be in Manhattan office, and we ventured west. We wanted to be close to JPL. JPL is, when it comes to robotics exploration of space, is second to none. It's a absolute powerhouse. The stuff they do is just amazing. So we wanted to be obviously close. Historically, Honeybee Robotics has been doing a lot with JPL on Mars exploration rovers and Curiosity and so on. So we wanted to learn from the best and be literally across the fence, and that's why we came out, and things really worked out. Back in 2010, it was just two of us. Now we coming closer to 150 people, and in fact we have to take over entire building next door to further grow. And we have a lot of fascinating missions coming up to the moon, to Phobos, to Titan, to Mars, and a lot of other concepts, like completely out of this world concepts that probably my kids will be working on.
Okay.
Some of these things will take decades, absolutely, decades, if not longer, to come to fruition.
So let's start with that, because that's exciting. Start with, right, I've heard recently, and I think I'm throwing it on every podcast, right, but there's vision, strategy, and tactics. Tactics, how does this particular drill into the soil? What is the research and the engineering marvels that allow that to happen? That's fantastic, but if you don't have vision and strategy, that's just a cool thing that you set on a desk. So I guess, zoom out for a second.
Mm-hmm.
You said the founders got bit by the space bug. There's a lot of different ways to get bit by the space bug. What's the main vision of Honeybee Robotics? And I think that'll probably tie into Phobos and cool future things.
I think vision of Honeybee is pretty much shared by everyone that works for Honeybee, and it's not just Honeybee. It's a lot of other space companies out there. It's all about discovering unknowns and really changing the world. You can obviously change the world and by developing new medicine, by developing more efficient cars and healthier food and things like that. To me and the folks working here at Honeybee, it's really all about looking out into space and wondering what's out there and whether one day humans could potentially settle on other planetary bodies like Mars, the Moon, and beyond. So it's just different type of curiosity and trying to change the world. It's like you go to an ice cream shop and you like vanilla, so you'll ask for vanilla. Your friend likes chocolate, so it's really it's what you like, right?
Okay.
And we're living in amazing times that we can have both vanilla and chocolate. So we can do space, and we can do EV cars, and we can do amazing, developing gene therapies and everything at the fingertips. Yeah. In fact, I told my kids, I wish I was born today. Okay, I wish I was born today and had opportunities to literally do everything that decades ago it was just far away.
Yeah, my heart goes out really to I think the phrase is orphans of the Apollo era.
Mm-hmm.
I mean, my dad doesn't quite fall into that. I think he was about 5 or 6 when he watched the moon landing. But the guys that were already in their mid-20s, 30s that were working on it,
yeah. These are things you'll never forget.
Yeah.
But the world is changing, and a lot of opportunities. One thing that, in fact, we're super lucky to witness is that 2 of the wealthiest people in the world, they're spending their own money on space, right? You have Jeff Bezos with Blue Origin, and Honeybee was just acquired by Blue Origin a couple of months ago to make his vision a reality, and then we have obviously Elon Musk with SpaceX, and so we're lucky. We're lucky that Jeff's vision is space, and Elon's vision is also space. And on top of this, there are many other billionaires and millionaires that are spending their own money advancing space technology. So it's absolutely new era.
So jumping into that, right? You said a second ago, right? One of the larger visions is that spread humanity out to the solar system, living on other planets, etc. Let's start with this. You posed a question to me a few months ago that just blew my mind apart, and it was regarding in the next 3 decades, should a trip to Mars be a one-way ticket or not? Mm-hmm. Talking about fuel costs and what that entails. Flush that out a little bit for the audience there, because a lot of people think of, go to Mars and die. That seems pretty intense, and who would want to sign up for that? You framed it in an interesting way, though.
Yeah, it's really economics, but one thing to also realize is we got kind of spoiled by transportation systems. Back a few hundred years ago, people would buy one-way ticket to come to America. Okay, They would board a ship, and they would know that this is one way. they're gonna have to come to America and make a living because there was no way of going back to where they come from. So it was fine. A lot of people, millions of people made this journey and made this commitment. So now, so you can argue, well, folks moving to Mars, they could make exactly the same commitment. They can make a commitment to go to Mars and stay there till they die. But there is another reason why it's going to be extremely hard for them to come back, and it's just pure economics. So a current cost of putting something on the surface of Mars can be traced back to what NASA JPL is doing, and taking big numbers.
Trace back there just because they've already
because
they've
they've done
so
it.
many examples. Yeah,
because we've done it successfully. They've done it every single time. If we take it for granted, but when we're sending spacecraft to land on the surface of Mars, everyone expects that this spacecraft is going to land. It's not going to crash. With expectation, but because of this expectation, there is also cost associated with this, and it takes a certain amount of hours to do analysis. It takes a certain amount of hours to run the test in order to make sure that the spacecraft is not going to create a crater on Mars, but it's going to successfully land.
Which is easy to do because Mars it's hard to get to it. You got to go crazy fast. Then you have to slow down, but there's not really an atmosphere to slow down, but there's enough of an atmosphere to make you heat up.
Mm-hmm.
It's a hard one to land on.
Mars is very, very hard. So let's talk numbers. Let's talk about Curiosity and Perseverance. Each of these rovers weigh approximately a ton. So, of average cost of putting this, rover on the surface of Mars was around $1 billion, right? Including launch vehicles, including cruise stages and sky crane and everything else. So sure, all right, $1 billion. If you want to put anything on the surface, 1 ton on the surface of Mars, it costs you $1 billion. Now,
and that's with current infrastructure, right? That's not assuming a Starship, for example, fully refueled.
Yes,
Okay.
It's exactly right. This assumes a status quo, the existing technologies, proven technology.
Got it.
If I want to put 1 ton on the surface of Mars, I can walk over to JPL, give them $1 billion, and I know a few years later there's going to be 1 ton payload put on the surface of Mars.
Nice.
Now we're working on something called Mars Sample Return Mission, which is not really a mission, it's a campaign of several missions.
Yeah.
But in a nutshell, there's going to be a couple of missions going to Mars, picking up rocks collected by Mars 2020 or Perseverance rover, and these rocks will be put inside Mars Ascent vehicle, or essentially a rocket, that will launch these rocks to the orbit, and Mars Sample Return Orbiter is going to capture these rocks flying around Mars and bring them back home.
Tracking.
So,
It's impressive.
Yeah, it's a very complex. It's probably going to be close to $10 billion across all the all the missions required to do this. But all right, fine. You don't really need Mars 2020 driving around Mars, picking up just the perfect rocks. You don't need a couple of things. You can descope certain things. All right, fine. Let's, for argument's sake, assume that the 1 ton that you put on the surface of Mars is actually a rocket with some kind of an arm that can pick up 1 kilogram of rocks, stick it inside the rocket, launch it to the orbit, and bring home.
Okay.
So let's say this entire thing costs $1 billion to bring 1 kilogram of Martian stuff. So now you can do the quick ratio. It cost me $1 billion to put 1 ton on the surface of Mars. It cost me another $1 billion to return 1 kilogram from a surface of Mars.
Okay.
So the ratio is 1 to 1,000. It's sort of like flying from Los Angeles to New York, paying $1,000 for a ticket to New York and paying $1 million to come back from New York.
Okay.
And
okay.
if indeed this was the case, not many people would go to New York, or people going to New York would go on a one-way journey, because they would know they have no money, no $1 million to come back home.
Okay.
So that's my point. My point is that the cost of returning from Mars is going to be significantly higher. All right, so you may ask, how much is going to cost to put a human being on the surface of Mars?
Hey, how much is it going to cost to put a human being on the surface of Mars?
All right, let's do some guesses. Call it, if I'm very optimistic, let's call it $10 billion. Okay, you develop technologies and life support and everything else, and for $10 billion, you can put a human being on the surface of Mars, and you're not gonna crash. Okay.
And you'll have an environment where they can live, right?
And you have an environment where they can survive.
Correct. Okay.
So now, if you apply a ratio of 1 to 1,000, so now it's to return this person back is not 10 billion, it's 10 trillion. Fine. Okay, I made a mistake. Let's say I made a mistake by an order of magnitude, or even 2 orders of magnitude. It's still a lot of money, even if I'm wrong by a factor of 100, right? And coming back costs 10 times more than going there. And going there costs $10 billion. Coming back costs $100 billion. At that point, you're going to start asking questions. Why? Why shall we bring somebody back from Mars if the reason to go to Mars is to settle Mars in the first place, right? So from an economic standpoint, there is no reason to bring anyone back from Mars. You can essentially keep on sending spacecrafts to Mars to increase the population, provide additional resources, some new technologies to make these folks live at a higher standard of living. So within a first generation, what you're going to create are Martians. We're not going to be humans anymore. They will be true Martians. And then there's going to be not just first generation, there's going to be second, third, and maybe after several generations, we develop technologies that will enable bring them back from Mars. Okay? At that time, we're not going to be humans, we're going to be Martians. They're going to look different. Okay? Remember?
Because of
gravity.
Because of gravity.
Because of the fact that they're going to be living in confined environments. They'll be born in a big can, all right? And that's what all they're going to know. They'll go out on some trips around, the local mountains, but they're gonna be enclosed in either pressurized rovers or spacesuits. But otherwise, these will be completely different, humans, and we're gonna be calling them Martians. And even we haven't solved virus problems. We've seen it in the past 2 years. We had COVID. These folks, they're not going to be exposed to any viruses that we humans are exposed to.
That's really interesting.
So they're going to come back, you sneeze on them, they're going to die.
Yeah, because that was the big issue with the two worlds interacting back in 1492 and thereafter. It wasn't, Europe didn't have germ theory. They didn't know that this blanket had smallpox and all these other diseases in them, but by push or by shove, disease was spread. And I think the stats were like, in the next 75 years, it was 98% of the Native American population over North and South America were just gone. Because diseases that they had never seen for 1 million years or whatever exposed. So, but I guess the rebuttal to that is, well, now we got better medicine. We got better, bacterial defenses and things of that nature. So maybe they could still interact and be friends. But I hear your point on the genetic decision. So, okay, well, that brings up an interesting distinction here, because Honeybee wasn't purchased by SpaceX that wants to go colonize Mars. It's purchased by Blue Origin that has routinely said they subscribe to the O'Neill philosophy of, why live on a planet when you can just live in a massive cylinder that has 1G and maybe close to Earth, et cetera, et cetera. Do you see, from your current perspective, right, longer in the industry, do you see humanity just following one of those routes, or kind of splitting into both? Of maybe we first go to Mars, actually maybe we first go to the moon. We can talk about that in a second. But there's some moon and Mars development, and then as the industrial base picks up, we've got these, humans or Earthers, whatever you want to call it, that are still in 1G.
Well, I think yes to all. We cannot just focus on one and be done with this. It's really important to focus on all the options that are in front of us. So near-term options is obviously some kind of space stations, and whether they rotate or not, it's question mark. The non-rotating space stations are actually pretty good. The humans are fine in a microgravity environment for extended period of time. You had folks on the ISS living there for a year or 2 years, and
doesn't it do a number on your bone mass though, and some muscles? And
it does. It does. You have to exercise, and we've been pretty good at figuring out countermeasures, food and exercise. But overall, I think if you hop between the space station and the Earth, you should be okay. And also, I would say that there is a reason to go to space in a microgravity, and that's manufacturing. That you can develop materials, fiber optic that doesn't have any losses, right? Perfect crystals, and for that reason, I think microgravity environment and space stations is really good. As we obviously grow and space stations gets bigger and bigger, you can start going into this rotating space stations, but then you have to worry about Coriolis forces and things like that.
Sure. Has to be large enough so that it doesn't, what was it, if you have a space station that's small, then the difference in the gravitational effect is really large between your feet and your head. And that, because you're 5'5", 6 foot, whatever, and then all the blood goes up there and you get real sick. So it has to be large enough so that the spin is decently similar of those 6 feet of height, kind of thing.
Yeah, and first time I learned about, I did read about it, but first time I realized, in practice, what does it all mean getting sick? It's flying with on a vomit comet, and or Zero G Corporation is a company that does these things nowadays, and you don't really get sick in microgravity. Okay, when when a plane falls down and you're in this falling down with aeroplane microgravity, you don't get sick. The only time you get sick is when aeroplane goes through a 2G pullout, so essentially bottoms out and has to come up again to fall down again.
Gotcha.
So during pull out, sort of like a takeoff, but it's up in the air, you go through 2Gs. And the best way to survive these 2Gs, which lasts half a minute or something like that, is to lay still or sit still. If you start moving your head, at that point you're gonna get sick. And so next time you drive fast car and you take a corner, move your head left to right, and you're gonna get sick. So that's why you're getting sick. When you have gravitational vector along one direction, and then you're trying to do something with your head and your inner ear, this is where your balance sits, gets all messed up, and you lose sense of which way is up. So that's why you're getting sick.
Gotcha. Yeah, I've seen some stuff on the recent Top Gun movie, where those guys trained Miles Teller, Tom Cruise, and the rest of them. Like, they were actually I don't think they hit 9 and 10 Gs, but they were actually at like 6, 7, at least 7 Gs. And there's a clip where Miles is like describing how you have to breathe and that just to like look around, and it's like real funny stuff. I have yet to be in a fighter jet. My dad did that in training back in the day. But it's taxing on your body. You have 7 of you basically standing on your chest. So we want to avoid that. Thankfully, there's no rocky planets in our solar system that will do that. Jupiter can't really stand on her. You'll fall right through the cracks. But zooming further out to the whole solar system, because you guys are doing some really great stuff up on the moon. But I think Hunter, one of the other guys on the team, we're going to have him on in just a bit and talk about that. So talk to me more about like the long-term vision, the things over on Phobos and all these other different tools the Honeybee is developing for, hopefully, an expansive future.
I'll start closer to home and maybe talk about the moon first.
All right.
Moon has water. Has plenty of water, which is ice, in the form of ice, because it's extremely cold, trapped in a South Pole, in a deep craters that haven't seen sun for billions of years. And that's where water molecules kind of got stuck and they never could come out. And another water molecule would come in, and let's say at the end of the day, you have a lot of water as ice at the bottom of the crater. So we're working on 2 missions. The first one is called Prime 1, and the second one is called Viper. Prime 1 is a lander, and Viper is a rover.
Do we know how much ice is down there, like roughly?
Yeah, on I can't remember quantity, but on average, is around 5-8%. So
okay, of the whole moon.
In the South Pole.
Okay, of the South Pole region.
Yeah.
5% mass.
On average, in these craters where you see a signature of hydrogen or water, so 5% of in a top, at least top meter,
right,
is water.
Because and it's top meter because currently we don't have instruments that can read really below that, right?
Correct. The neutron spectrometer and can only sense down to 1 meter. It's more complex than this, but because
sure,
you have to learn about like epithermal thermal neutrons and the propagation and but bottom line is from a neutron spectrometer, 1 meter, top 1 meter. So we know within where you see ice or hydrogen, approximately 5% of this is water. And it's also thanks to L-Cross mission from Ames that
which was 2012.
I think around close to a decade ago, impacted Cabo's crater and created plume, and spacecraft essentially flew through this plume and measured how much water came out, and that's how we have pretty good number.
Gotcha.
The L-Cross probably excavated much more than a top meter.
Sure.
And so bottom line is Viper and Prime One, they are equipped with 1 meter drill called Trident that Honeybee is building, and both missions have a mass spectrometer, and Viper, in addition to mass spectrometer, has near infrared spectrometer and neutron spectrometer. So these two missions, the goal of these two missions is to characterize how much water there is, and also characterize how much other volatiles there is there are in the South Pole, because it's not just water. There is carbon monoxide, there is carbon dioxide, there is ammonia. So if you look at what comet is made of, pretty much most of the stuff you can find in the South Pole and North Pole of the Moon, because the water came from comets.
Right. That's comets
impacting, yeah.
Spill their guts. And okay, so you said it has the drill, which has its own technology we can get into, but then on Viper there's a set of mass spectrometer, neutron spectrometer, and what was the third?
Near infrared spectrometer.
Near infrared. What do the three of those do?
So the neutron spectrometer is looking for thermal and epithermal neutrons that originate down to a meter depth, approximately. So they're looking essentially for hydrogen. And the hydrogen is proxy for water because it's H2O. And if you find a hotspot, high hydrogen signature, then there must be probably water there.
Are there other elements on the moon that hydrogen readily bonds to?
You may have hydrated minerals, but not very much on the Moon.
Okay.
So
if you see hydrogen, it's water.
Pretty much water.
Gotcha. All right. So that's the hydrogen. That's the ion one, and then there's the mass spectrometer, which.
That's right. And so once hey, there is a hotspot, at that point you can deploy the drill, and the drill goes down and brings the icy soil to the surface, and then mass spectrometer can sniff all the volatiles, all the ices that are escaping from a material that's brought to the surface. So on the Moon, when you expose something, it's gonna literally sublime away. So things vaporizing on Earth, on the Moon, they subliming. They go from ice to vapor, and that's what mass spectrometer is sniffing. And near infrared spectrometer is shining a light on a material called regolith that the drill is bringing from subsurface. And by looking at light coming back, it can also determine to some extent certain volatiles and also mineral content, what the material is made of, the fundamental minerals.
Okay. So the data that we have on the moon, it's good for the spot locations, but those spot locations in the past, have we ever drilled down to a meter before? With all the different Apollo missions, I'm pretty sure those were just hand tools, right?
Yeah, Apollo 15, 16, and 17, they actually drilled down to 3 meter depth on each one of them and brought 3 meter long core that's now sitting at NASA Johnson in a creation facilities. And every so often they open up one of these cores to investigate. So we've done drilling with humans. We've done robotic drilling. In fact, very first drills were sent by Soviets on the Luna 16, 20, and then on Luna 24, they were all sample return mission. Luna 24 brought a sample from Mare Crisium down to 2-meter depth. And
Wow.
just recently, Chang'e 5, Chinese mission, also brought the sample. They used a very similar drill as Luna 24 drilling system. The goal was to go to 2 meters, but the drill got stuck at the meter depth because of the pebbles, like small rocks. And so at the meter depth, the mission stopped, and they brought sample back from this top meter. So some of these robotic,
Gotcha.
drilling has been performed, but no one drilled in the South Pole.
Sure.
All the drilling and mining and in fact all the missions went to the somewhat warmer regions on the moon, and none of them went to the southern polar regions where we have high probability of finding ice.
Gotcha. So, if you're drilling on the, the latitudes that are further up on the moon, and there's less hydrated materials, the moon is still, it's very dusty, it's very densely packed. Are there different problems that come with drilling in an area that has basically no water versus drilling half water concrete moon dirt?
Yeah, on anywhere else, so top 10, 20 meters of lunar surface has been literally pulverized by impacts,
Yeah.
meteorite impacts. So essentially a rock hitting a rock creates more rocks and dust, right? And then another rock comes in, hits a smaller rock. So over billions of years, lunar surface essentially became pulverized. In fact, most of 50%, if not more, of lunar soil is sub 75 microns. So it's the size of a human hair. It's super fine.
Wow.
It's powder like. And so it's when you drill into this, it's not drilling into rock. It's really drilling into like sand on a beach, right? Because it's all powder, it's all granular material.
Okay.
But in the South Pole, that's a reason why our drills have hammering action or percussive action, because we just don't know whether ice that's in the South Pole froze to form concrete hard material like in the East Coast in winter, or in Alaska, right, when you have permafrost, where you have 10%
Gotcha.
water, and you have soil, and it's no different than concrete, right?
Yeah.
So we don't know whether it's something like that, or whether the ice has also been pulverized by impacts, and it's also granular. We just don't know.
Gotcha.
We don't know which of factors dominated, because in one factor you have sintering, where ice molecules kind of stick together to form ice cube, or whether meteorite impact was effective enough to keep on breaking these ice cubes into smaller ice cubes.
Into
right?
smaller sections. Okay. Yeah.
So the drill will tell us. This is the only way to know drilling. And if we drill and we see we need a lot of power to drill, yeah, we're drilling into concrete. If we drill and we need 10 watts or 20 watts, like LED light bulb, then we know it's relatively soft.
Gotcha. Okay. And again, so the way this drill is very similar to like mining or oil excavating drills, where in those cases you've got a drill bit and then a shaft above it, and if you want to go deeper, you just put another shaft in there and extend it further down. Is that how these Viper drills are working, or are they just going to the 1 meter depth?
It's just 1 meter depth.
Okay.
The adding another section is possible, but
Sure.
you have significant increase in complexity,
Yeah.
in the robotic complexity.
Makes sense.
And because you have a rover, you'd rather spend time traversing longer, longer distances, as opposed to spending time adding these drill strings and go deeper and deeper and deeper, right? And
Gotcha.
then potentially risk getting stuck forever. So that's why we said, well, this is not gonna be the first and last mission. This is gonna be one of the missions that we send to the moon. The goal is to go as far as possible to determine distribution of ice. So it's not just single location, but is this distribution the same everywhere we go, or some dry patches, or or ice-bearing patches. Right now, the pixels that we have from orbit are huge, kilometers, miles big. So we want to reduce this, granularity, as to speak, to
get higher fidelity
10
data.
meters, maybe every 100 meters kind of thing.
Okay, just drill, travel, back and forth there. The South Pole, though, those craters are pretty darn steep. I've heard some other guys talk about, and it's too late now. We've been too committed, but the North Pole still has permanently shadowed regions, still probably has ice up there, but it's a lot more gradual craters on the way in. South Pole's not like that. Those things are 12 to 29, 30 degree inclinations.
Mm-hmm.
That's probably a whole host of challenges for a rover to maintain as it's going down there. How do you mitigate that when, especially if the mass, or I guess the weight of the rover is now reduced by 1/6, and you're drilling?
Yeah, we're not gonna drive all the way down to the bottom of the crater. We're gonna take a dip in permanently shadow regions for a couple of hours and come out. So we wanna crawl before we walk and before we run. But yes, very steep. But Curiosity rover was designed for, is it 25-degree slopes? So we know how to build stuff for steep slopes, and folks who love monster trucks, you can just see what these puppies can do, right? They go up super steep slopes, and I don't think this would be, from an engineering standpoint, a showstopper.
Okay, fair enough. So, and again, right, the Viper setup that this drill is attached to, that's not collecting samples that then we would return. It's drilling them, pulling up the data, and then using those 3 different measurements to say, this is the data. This is what's collected. Correct.
So the drill essentially, it's like it has an auger which brings the cuttings to the surface, or brings material to the surface, and you can look at it. But another mission that we're flying to Mare Crisium and the Schrödinger Basin on the far side of the moon has different type of drilling system. The drill is size of a shoebox and goes 3 meters down. 3 meters down and the size of a shoebox. And it's completely different technology from more of these traditional technologies that we just described. It's called the coiled tubing. It's actually used in oil and gas, and not many folks know that oil and gas is using this technology. Coiled tubing. It's in oil and gas. It's 2-3 inch diameter steel or composite tube that sits on a drum and goes through something called injector, which essentially turns this tubing, straighten it out into a straight pipe. And that's how you lower this entire drill pipe down. So there is no sections. It's a single coiled tube. It's sort of like a garden hose which you pull out, and and becomes straight.
Are these the things that? So like for the visuals, right? It's a flat sheet, and then when you inflate it, it like balloons up.
No, it's always a tube.
Always a tube.
It's like a garden hose. Your garden hose is always a tube.
Yeah.
And
we fit that inside a shoebox.
Yeah. For this particular drill called Lister, which is a heat flow probe, where the tube is something like 6 millimeters in diameter, so it's actually quite small. Quite small, and takes 50 watts to straighten it between a set of rollers. All right. Gotcha. Going back to garden hose analogy, our muscles are strong enough to essentially pull a garden hose, and so it's straight. So if you have a steel tube and you're a strong guy, right, you can do it the same, or you can pull it between the rollers and make it straight.
Gotcha.
So that's something like this that we're using for these two missions. And instead of having a drill bit, we're actually using compressed gas. And compressed gas is like an explosive on the moon in a vacuum. All explosives on Earth, the only thing they do is they generate a lot of air, right? That's why they're explosives.
Okay.
On the moon, compressed gas is like explosive because it expands into vacuum.
Yeah.
So we're using this explosive nature of compressed gas in vacuum to essentially excavate a hole. We're sending this compressed explosive gas down in the bottom of the hole. It blows the regular out of the hole at 10, 15, 20 meters per second. Super fast. And that's, tiny thing. Right now we have concepts that would make a 100-meter hole on the surface of the moon using very similar concept. Yeah, and that's possible.
Is there a way, like when you're doing this, I'm assuming that gas is just lost to the atmosphere.
Yeah.
Okay.
Yeah.
So it's with that shoebox-sized thing, you can compress the gas down, but it can go down to 3 meters. Probably gets like 5 or 6 different attempts at 3 meters, and then it's out of gas or something like that.
Yeah, we budgeted enough gas to allow us at least 2 to 3 3-meter holes.
Okay.
So we've got plenty of gas, and the tank, the tank is size of a Coca-Cola can, so you don't really need a lot of gas. In fact, for 1 gram of gas, you can lift around 100 to 1,000 grams of soil.
That's okay. That's
so
the measurement we needed.
This is the ratio, right?
This
is the ratio. So we became very conservative. We said, well, we're gonna probably do 1 to 10 to be on the safe side, and we carry a lot of gas.
Okay.
For future, if you want to go 100 meters down or even deeper, you do not need to bring gas with you. Yeah, the propulsion, if you think about it, propulsion systems on landers, they already have gas. They use nitrogen, argon, helium to compress propellant. So when you touch down, this gas is normally vented to vacuum, but you can tap into it and you have gas for free.
That's not bad.
So yeah, you don't even have to worry about tanks because the lander is going to provide it to you.
So so a rover comes and lands down on the moon, and it now has 50% of its gas left because it still has to leave, and because it only has 50% gas left, it doesn't need as much of the argon or whatever.
Yeah, landers most of the time they do not leave. The
that's right. The bottom
the bottom
element.
part stays.
Gotcha.
Yeah, if you have a lunar ascent vehicle or return vehicle, it's an upper section with its
Gotcha.
own propulsion system
Different
and so
story.
on. Yeah. The bottom part with the big tanks. So actually, you don't really use gas. We only use gas to compress propellant, but you don't really lose it as such. It's still sitting in the tank,
Gotcha. Okay.
so you can tap into it.
So if we were to go to what at some point will be deemed historic sites of all the Apollo programs, just
Scavenging, yeah, why
scavenging, fill up the tanks.
Why not? In
Space
fact,
pirates.
yeah. In fact, think about it. Some propulsion systems they have hydrogen and oxygen,
Yeah.
right? Which is also a gas.
I could use some oxygen.
Yeah.
That would be
Here we
nice.
go. So we can tap into it and use it for our drilling and mining
Okay.
system. So yeah. So there is a way to make things to do things efficient or on a cheap.
Okay.
So that's the moon.
Yeah. So, but you're doing some other cool drilling stuff. Not only just like sample, but also like resource extraction over on Mars, right?
Yeah, on Mars we developing a payload called Red Water. It's a deep mining system. That it goes tens of meters below the surface, and Mars has these ice sheets. They 10, 20 meters below the ground. You have literally glaciers. Which extend like 100 meters, 100-meter thick, and so you can drill down and 10 meters or 20 meters, and then you're in ice.
Wait.
Pure ice.
Question though. So, how do we know on Mars that 10 meters down there's oceans of ice, glaciers of ice, and on the moon we have no idea what's below a meter?
Oh, because we took picture of this.
Okay.
From Mars, we have pictures. We have pictures of these, big glaciers covered by, 10, 20 meters of regolith.
Okay, but so in infrared, in neutrons,
No.
in visual, but it's under 10, 20 meters of soil. So how did we?
Because on good question. Yeah, you have you're actually looking on the side of like craters, and that's where you see exposed.
So like
exposed ice.
if you go to the Grand Canyon, you're like, oh look, sandstone. Here's where the dinosaurs died. Same sort of thing you can see on multiple craters on Mars.
You see on multiple areas on Mars, including Arcadia, Polynesia, which is one of the
Big spot.
big spots. Yeah,
Tourist destination.
this and also the other. You can actually see a signature of ice at the bottom of a relatively recent impact craters.
Oh.
Yeah, apparently, if Viking could drill meter down, it may have potentially encountered ice.
Wow.
Yeah, if Viking could drill, but obviously it couldn't.
Okay. And when did Viking go? Back in.
I think it's 80s.
Okay, a long time ago. Gotcha. Okay, so personally, I'm more like predisposed to the moon just because it's right there. I get to see her every night. Speak sweet nothings to the moon. I can't see Mars. She's really far away. But, I mean, there's a lot more resources. The moon's got a ton of resources, and we can always chat about that, and I'll have other guests on the show. But talk to me more about Mars, right? Because that's where we started this. That's where a lot of people want to go and die. So you're sending equipment there to drill down and access that water.
Right.
Red water? You said Mars, red.
Yeah, we call it red water because it's
Red water.
Mars, and
Tracks.
color red is come from iron oxide. So we're gonna drill down to get to ice, and then we'll heat up ice and we'll melt it.
Okay.
So we're gonna essentially form a bubble, molten, liquid water in the ice, and we'll pressurize borehole, open a tap, and water and the pressure is gonna flow to the surface, sort of like geysers on in Yellowstone. Same idea. And we actually, this is not theoretical analysis. We've done these sort of technologies. We've done these sort of tests under Mars conditions in our big Mars chambers. We had a drill like this. We drilled down into blocks of ice, and we melted ice. We actually put a dye to make it red. We pressurized the borehole and open a tap, and then water would flow into a cylinder inside the vacuum chamber as well.
Gotcha.
And so it's actually possible. It's not it's not sci-fi. It's engineering, and fundamentally physics works.
Are there mass constraints for the Martian one to drill that far down and get the water?
No, tens of meters is not that deep. Things like this would weigh hundreds of kilograms.
Okay.
So it's not tens of tons.
And we've already hundreds of kilograms, and we've already put 1 ton equipment on the Mars. Okay.
And with a Starship, we should be able to put tens of tons on the surface of Mars. So I don't think mass is gonna be a driver here. Driver is gonna be things will be breaking. Okay. And the water that we will mine and extract, it's not it's not a spring water. Okay. It's not you go to a mountain and it's fresh, delicious, and you can drink it.
Is it dirty?
It's dirty, and it's actually it's gonna have some salts like perchlorates, perchlorate salts, and so you will have to clean it.
Yeah, those perchlorate salts, those aren't good for your skin.
No, they're not very good. In fact, everywhere you look, the only water that's nice and delicious is the water that comes from from clouds and gets down into the ground and gets cleaned by soil, filtered out, and but it's just like ocean, In fact, all the water in the solar system is salty water, like our oceans.
Really?
Mm-hmm.
Out in like Uranus and Neptune that have tons and tons of water, that's all salty stuff.
Well, like Europa and Enceladus.
Okay.
Yeah, it's gonna have salty water. In fact, Mars apparently has also lakes in the South Pole. Close to a mile deep. In fact, we just recently found lakes on Devon Island, up in the high Arctic, Canadian Arctic. Half a kilometer down, these lakes are hypersaline, so they liquid at minus 10 degrees centigrade.
No way.
And the reason why I'm mentioning it, because our crew just came back from there. They deployed a melt probe as a very first test to get down to these lakes 500 meters below the surface. So we went down a couple of meters. It was successful, and we had to leave because the weather was. We flew with a helicopter, had a couple of hours on the surface of ice, and eventually had to head out. So we didn't have time to go deeper.
Okay, so you got plans on going back in the future?
Next year, every year, we're going back.
Okay.
Every year we're going back.
Just because there's really short cycles where humans can even operate up there?
Yeah, it takes some time to develop technology. It takes some time to put the expedition together. This time around, it was kind of more of a scouting expedition. So we had a helicopter that would come and drop us off and then bring us back. But next year, what's probably going to happen is we'll go there with entire camp and stay there for a week or 2 weeks, and then do more of a melting.
Okay, gotcha. So if there's already lakes over on Mars that are just hypersalinated, I guess what's an easier if you flash forward to humans trying to live there, what's an easier problem to solve with current tech? Is it let's melt the ice with some chlorates up at the top, or desalinate crazy ice? Well, get to the liquid ice, the liquid
lakes.
water
Yeah.
lakes, and then desalinate that.
These lakes are very deep.
Okay.
It's much easier to drill shallow hole and melt ice than it is to drill deep hole to get down to some kind of a lakes.
Okay. Are there regions on Mars that are, that we've seen from craters that are more heavily pocketed with these ice sheets closer to the top?
Yeah, we found them in couple of areas. There's actually a paper that was published a few years ago that essentially delineates where those features have been located. Mind you, we've been taking a lot of pictures on Mars.
Yeah.
A lot of pictures. There is so much data. It takes time to process all this data. That's why NASA is developing AI. So up to recently, you had graduate students looking for the pictures and looking at data, looking at features, and trying to make sense of this, comparing and so on. And the amount of data we generate each day is crazy. I mean, think about how many pictures you have on your phone, right? And imagine that each of those pictures have to be analyzed, right? Just like on Mars. So it's a ton and ton of pictures. So we have to develop AI to look for certain features instead of relying on grad students to do it.
Analyze as in like, hey, this rock means this that you see, or analyze as in like back to the old classic of we have to let the film develop, but for a digital version.
Oh, more in you already have a photo and you're trying to see what, let's say you see one rock formation in certain location of Mars, and you're wondering whether these same formations can be found somewhere else on Mars, right? There are some features that, for example, have been created by probably flowing water, right? Sure. And then you're trying to find similar features. So we've been looking with our own eyes, and then we go, oh, here you go. It's a river delta right there. So it's much easier along the same lines if the AI, you load all the photographs, and the AI tries to look at patterns and certain features and lava tubes and things like that.
Okay. All right. So we've covered the moon. We've covered Mars. What about all those other cool rocks out there?
I'll tell you that one thing that is going to be really cool is Europa.
Yeah.
So Europa.
And where is Europa?
So it's a moon of Jupiter.
Okay.
And it's one of 4 Galilean satellites, right?
Which are the bigger ones, right?
Yeah, 4 biggest moons like Ganymede, Io, Callisto, and Europa.
Gotcha.
And Europa is pretty fascinating. It's size of our moon, okay, but it has more water than we do here on Earth. Which is kind of crazy to think about it, that we are not special when it comes to like how much water we have. In fact, we don't really have a lot of water on Earth.
Wow.
Yeah, the moons out there, they're not even planets, they're moons.
Wow.
And they have more water than we do. So this moon, Europa, has around 15 kilometers or 10 miles thick ice, followed by ocean.
Wow.
And this liquid ocean may have some life, some traces of life. It's not gonna be fish. It's gonna be simple cell life.
Sure.
But a mission that would penetrate through 10 miles of ice and get down to the ocean would be really, really cool.
Yeah.
We are developing, so the reason why we're going to Devon Island is to learn how to do this kind of missions. And these missions would have nuclear reactors, so
Sure.
you need a lot of heat.
Mm-hmm.
These missions would be the probe that we're actually developing right now for NASA is called SLUSH. It's called Search for Life using submersible heated drill, or SLUSH.
Okay.
Slash D.
Submersible.
Yeah.
So like a little, so it drills and then it descends into it like a submarine?
It's sort of like this. Yeah. So imagine you have a torpedo. Okay.
Okay.
A torpedo that's, say, a foot plus in diameter and maybe 15, 20 feet long.
Okay.
Right?
Okay, gotcha.
And this torpedo has nuclear reactor at the bottom. And then above nuclear reactor, it has a generator system that converts heat from nuclear reactor to electricity.
Mm-hmm.
It has batteries, it has computers, it has communication systems, it has some motors and drill bits and this kind of stuff, right?
Gotcha.
And as it penetrates down in ice, it breaks up the ice and turns it into a slush.
Okay.
And as the probe penetrates down, the slush above the probe will slowly refreeze. So your probe essentially penetrates by making like a bubble around it,
Yeah.
right? So this bubble with a probe inside it kind of goes down, 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 and
Just sinks.
just slowly sinks. And what you have, what you leave behind, is a foot diameter refrozen ice, okay, above
Yeah.
you. So one of the ideas we have is essentially to leave like fiber optic
Okay.
for communication.
I was gonna ask, like, how do you get data through that?
Yeah, you can do it with fiber optic, or you could also do RF communication if you have. It's more complex. It's fun stuff. You have like a repeaters that you leave in ice behind you.
Oh.
But this journey is gonna take 2 years at least to get down to the ocean
From landed
from landed.
to 10 miles down, 10 kilometers.
10 miles. We don't even know actually whether it's 10 miles or 10 kilometers. We'll find out.
Okay.
But it's a long trip. It's a long trip, and eventually you get down to the ocean, and that's when fun is gonna start, because you're gonna be tasting this water and looking for microbes. We've done similar thing here on Earth, believe it or not. There are actually lakes at the bottom of Antarctica.
Really?
The most famous lake is called the Lake Vostok, which was it's a couple of kilometers down, and Russians managed to drill down to Lake Vostok, and water was under pressure. So the moment they broke into the lake, there was an inflow of water into the borehole. So that's how they managed to capture some of this water and analyze it.
Nice.
So
And that was salty, very, very salty.
oh, I can't remember.
Yeah.
I think it was a fresh water. I don't
Okay.
think it was a salty water. But so there are these analog locations here on Earth where we would have to go and test it out before we go to Europa, right? If we can't go to Devon Island and go half a kilometer down
Sure.
and get down to the ocean on the first trial, there's no way we're gonna make it on Europa,
Mm-hmm.
right? So this is what we're doing right now is a very first step in developing these sort of technologies, and it's gonna take decades. It's
Yeah.
gonna take decades to get
Because
there.
the mass of this thing, couple tons, tens of tons.
Oh my God, the amount of technological breakthroughs you have to do to pull it off is just unbelievable.
We don't even know how much it's gonna weigh yet.
We don't know how much it's gonna weigh. We don't even, we cannot comprehend the complexities. But I can tell you that technology we don't necessarily need to solve all the problems, because a lot of problems are being solved for us by adjacent markets.
Okay.
So let's say you have oil and gas. Okay. In oil and gas, every day they go down to areas that require electronics to work under immense pressures and temperatures. You have electronics that works at 200 degrees centigrade every single day. Not a problem, okay? Few decades ago, it would be unheard of, but we figured it out. And this technology can be used for these probes that will go to Europa. So you don't necessarily need to solve all the problems. You just have to keep a tab on what's going on around you and use this technology.
Okay.
Look at the very fascinating mission to Titan, the drone that will explore Titan. We're actually building a mining system for this mission called Dragonfly.
Okay. A mining system attached to a little propeller drone.
Except it's not little. It's size of a car. It's size of a car. Imagine Perseverance rover flying on Titan.
So you're saying flying cars do exist?
Flying cars will exist the moment we land on the surface of Titan.
Almost there.
And almost there. So this mission is only possible by all the technological breakthroughs that created drone market here on Earth.
Yeah,
right?
Sure.
And all the IMUs and electronics and motors and stabilization and making sure that you can actually fly level, right, and the straight and level.
Mm-hmm.
All this stuff was done by drone industry, and we essentially borrowed it, and we're gonna be using it on Titan. So super fascinating. Again, we didn't have to develop this, right?
Gotcha.
So it's really important to to keep a pulse, to keep a finger on a pulse, and look around and see what other industries are doing, where electronics is going. Computational power, actuators, new materials like bulk metallic glasses that are coming up. So all of this stuff is gonna make it possible.
You said bulk metallic
metallic
glasses.
So it's a metal that doesn't have a crystal structure. So all metals they have a crystal structure, and the bulk metallic glass does not. It's glass, and the glass is amorphous. Okay, no crystal structure, and what this means is that its properties are different, and in many cases are much better. So it's significantly harder than wear resistant than traditional metals.
Nice.
Yeah. So these are the things.
So ancillary technology,
pretty much. Yeah.
That's helping all this develop. Okay, so with all that we've covered so far, like there's a lot of examples of cutting edge research that you guys are doing and getting contracted by NASA and other agencies like that. Say, hey, we really want to be able to have this experiment. Can you build us the technology? The future of Honeybee, is it more research based, or is there ever a point where it's like, hey, we want to take this and now use it for mass commercial activity? Like what's that future look like?
It's both. There's no commercial without a lot of this R&D.
Sure.
In fact, if you think about maybe 1% of the technologies that we develop can be commercialized. The ratio is actually pretty low.
Wow.
So it's much cheaper to steal ideas from somebody else, right? And But by developing technologies, we learn about what works, what doesn't, and so far I think we've been pretty successful, commercializing technologies. And by commercializing, we mean sending to space, or even using here on the Earth. So, there are a lot of kind of spin-offs from technologies that we develop for other planetary bodies, whether it's software, whether it's electronics, whether it's different type of sampling.
Okay.
The all the instruments, right, that we develop for space exploration has to be really, really small, right?
Yeah.
And you need really tiny amount of sample. Here on Earth, you can use these instruments, right? If you can get the same data from something that size of a microwave, you can take it with you wherever you go, right? So we're scaling down instruments the size of a room and turning them into instruments the size of a microwave or even smaller, right? And that's where the major breakthrough comes
Okay.
from.
All right, tracking there. One of the phrases that gets tossed around in the industry, especially by NASA folks, is this moon to Mars. Moon is a gateway to Mars. And I've heard from very passionate people on both sides that is either the absolute correct way to describe the future, or that's complete hogwash and bonkers, and it limits the development mentally of the moon. Where do you fall on that sort of aisle division?
I would say that there are benefits to go to the moon and before you go to Mars. But you have to go to the moon, and I think we have to go to Mars. So it's not like moon is a stepping stone to Mars. No, you not go to the moon and then you leave moon to go to Mars. You go to the moon, you settle the moon. There are economics that will help to sustain this human presence on the surface of the moon.
Yeah.
And then some of the folks will go to to Mars. It's like first folks coming to America. Some of them stayed along the coast, and some of them ventured west.
Yeah.
Right. And moon is some people will stop at the moon, and some people will continue to go to Mars.
Fair.
So I don't think it's that simple, like white or black here. It's actually gray area.
Okay, that's fair enough. Yeah, and I feel like there's a Venn diagram of technologies and research developed for the moon, and that are developed and applied to the moon, and technologies that are developed and applied to Mars. And there's a decent amount of overlap. It's not complete by any chance, by any stretch of the imagination, but there's quite a bit of overlap between those. Have you found that in just your own drilling equipment, in that development? Like the R&D dollars we put into preparing for Viper is really going to help us on red water?
Oh yeah, absolutely. There are some subsystems which we pretty much taking build to print from between red water and Viper, and some of the things we obviously making changes to. Also, developing any technologies. There's one thing that we shouldn't forget, and that's that human beings develop technologies, and these human beings, they have to be trained, educated, develop technologies. That's why we go to school, in the first place, learn math and sciences. It takes a long time to develop it, and people come in and people retire. We need opportunities for folks coming out of school to get educated in building stuff. All right, so they can continue this journey. And That's why I think this going to the moon is not gonna be we're gonna go there in the next 10 years and everything is gonna be done. No,
Hmm.
we're gonna go there and then we have to keep on improving. So there's gonna be continuous
Yeah.
influx of people and new blood to develop new technologies, better technologies, life support systems, mining systems, and to set bases on the moon and then Mars.
Gotcha. Yeah, I mean, I've noticed on the education side, there's, from not being an employer of a ton of different people right now, but there's quite the influx, it seems, of 27 to 21-year-old engineers and space people entering into the marketplace.
Mm-hmm.
And yet at the same time, I hear all the time about a labor shortage within the aerospace industry, within the space industry. Is that just because we need to move faster? We're trying to catch up with China? Are there other industries that are kind of cannibalizing that? Where do you think that fits into the piece of the puzzle?
Yeah, well, it's a good question. I think that space in general, space industry is driven by the fact that space is slowly becoming next frontier.
Hmm.
And what we're seeing is that the big market is a communication market.
Okay.
So you have
Satellites. Yeah.
You have satellites. You have communication satellites. The right now Amazon. Sorry, let me just drink some water.
Yeah. Water break. You too, listening in.
So what you see now is space as a next frontier, and companies like Amazon, for example, developing Kuiper satellite network, communication satellite, SpaceX developing Starlink, and OneWeb, which started all of this. Eventually, there's gonna be 50, 100,000 satellites in our orbit, providing high-band communication, so you can fly an aeroplane and do a video WebEx with folks on another aeroplane. All right, that's totally feasible. So it's a commercial market. It's gonna be a huge market, but it's this market that right now is pulling a lot of young engineers. All right, so the competition. So some of those folks essentially go to build these satellites. There is other folks that go to the sort of exploration business, like us here at Honeybee.
Okay.
And obviously you have a bunch of other folks that go into rocket companies.
Mm-hmm.
And believe it or not, there is over 100 rocket companies in US.
There's so many.
Yeah, it's plenty. So imagine, 100 companies.
Stop making rocket companies. Just please, just don't make another.
And let's say each company is at least 100 people, right?
Yeah.
So do the math. You have tens of thousands of people, right, in building rockets. Some of these companies will never make it, but some of them they will, and they just some great companies out there.
Yeah.
So a lot of this is driven, by this, by this economics and the future payoff. I want to finish, with. Just want to emphasize the importance of training people. We have a very strong internship program, but when I was a student, I was sponsored by a mining company in South Africa called Anglo American and De Beers. It was this big gold diamond company, and so every summer I would spend 2 months working 12,000 feet below the ground, or a few thousand feet below the ground, and would go back to school and would approach all the subjects and engineering subjects from a slightly different angle, more practical angle. Yeah. And eventually, after school, I ended up working in those mines for a couple of years. It was just unbelievable experience, learning true engineering, seeing things breaking, And this really set me up for developing these things for space. And we trying to open the same opportunities for students to come here, 10, 15 of them at a time. Spend a couple of months and learning what engineering is like, what things work, what things do not work. And our future essentially is in the hands of folks that are going to school right now and will be graduating soon. We really need to keep going.
Yeah.
And people is essentially our future, so it's important to invest in our future.
Absolutely. I mean, I think that's one of the main reasons I'm doing this is because China produces more engineers every year than we have in our entire workforce.
Yeah.
I don't have the brain to be an engineer. I did finance somehow, and now I just talk to people, and numbers are involved in sales, but we need those engineers. So keep it up, guys and gals, please.
Finance, one thing. Other thing that people don't learn in school is that money is critical.
Oh, yeah.
And I usually say that difference between a good engineer and a brilliant engineer is nothing less than a brilliant engineer can do it for less.
There it is.
Okay.
Yeah.
It's everyone can build stuff, but if you can build it at half a price, you're a brilliant engineer.
So as you're going through your capstone project, try to finish it early. Take a step back, come back and go, how could I reduce complexity? How could I make this cheaper, etc.?
That's right. And that's the only way we can actually explore space. If we can build stuff at half the price, we can launch twice as many things. Simple math.
I like it. Well, we'll pause here, and then we're going to bring Hunter on as well. But for engineers and stuff out there, best way to get in touch with you guys for that internship program, or what is just the
Reach
website?
out to us. Go on the website, send us email. We are on Twitter, we Instagram, social media. You'll find us.
Do you have a TikTok?
Not yet. Next is gonna be TikTok.
All right, little video of the drill going down, the drill going up, things of that nature.
On Devon Island.
There it is. That'll do the trick. Sure. Awesome, Kris. Well, hey, really appreciate it.
Thanks for having me.
Absolutely. Thank you so much for tuning into the show. We greatly appreciate it. If you got some value out of this video podcast, drop us a like, comment, review, anywhere it is that you are listening or watching the show. That's right. If you did not know, this is a video podcast. So if you want the whole experience, including the funny faces that I just made into the video, check it out on Spotify or YouTube for that full experience there. I am at Vincent Marolli on YouTube and on all social media platforms. Vincent Marolli, MIROLLI. Check out the description. Kind of sounds like cannoli, but that's outside my control. So at Vincent Marolli on everything but the TikToks. Not jumping on that train. Don't want to give China any more of my information. They got a lot. Next time, we are going to have Daniel Faber on the show. He's an incredible CEO in the space industry, and his company, Orbit Fab, they're making gas stations in space. Yeah, chew on that. You got 2 weeks until that next show, so get your pencils ready for your notes. It's going to be a good one. Until next time, may the God of hope fill you with all peace as you trust in him, so that you may overflow with the power of the Holy Spirit. That's some encouragement from Romans. It certainly encourages me. I hope it does for you as well. Till then, ad astra.